Right. So let's now get to our last part of the lecture. So this part is on an example of a real-world convolutional neural network. So this is an example in which we will take basically an image and do an image classification. And specifically, we will be looking at the network called AlexNet. So AlexNet is basically, I would say, the network which showed the feasibility of deep learning. So this was 2012. And really after 2012, the deep learning and also more general machine learning has basically really taken off. And so the main reason that this AlexNet was working so well, and actually also several very similar architectures around the same time, is thanks to the use of GPUs for computing those convolutions. So we saw those convolutions in the lecture already. And the problem with them is, you recall, like if you have one of these filters, you have to compute a dot product with the image, and you have to do that in many places. And this is a lot of computations, all right? And the GPU is able to do a lot of these computations in parallel, and therefore able to apply the convolution very fast, right? So it can parallelize the task very nicely. And so basically what they did in this work is really just make use of that GPU computation power which existed at that time. And what was also very remarkable is basically how well it performed. Right? It performed a lot better as any of the systems which were using any kind of manual feature extraction and so on. And it got basically a top 5 error of 15.3% on a dataset which has 1,000 categories. So if you've ever done any kind of 1,000 categories is the same as 1,000 classes, right? So if you have 1,000 classes, the probability of just by chance having something correct is extremely small, right? So if you have that many classes, getting that kind of performance is really significant. And by some, this network is actually considered as a real start, the real time when industry started adopting neural networks for real things. What is also remarkable is that this is just a variant of an older idea, right? So this is just a sort of re-implementation of a work from 89, right? So it's a work which is by now about 30 years old, which was then applied on handwritten digit recognition. So many of you have now used that sort of data set. And the point was, it was basically using the same technique, but then basically doing a clever re-implementation on GPUs. So what I would now like to do is to basically just look at that network and see what it is composed of. Okay, so what we here see is basically the first image which gets fed into the network. So we have here this volume here. So we have an image which is 227 pixels by 227 pixels. And it has these 3 layers, basically the RGB as we saw it. Now, the first thing which is going to happen is that we are going to apply a convolutional layer, exactly the same way as what we saw. And here this convolutional layer will be, this convolutional filter rather, will be of dimension 11 by 11, right? So you have an uneven number, as we also had, and this one is going to be applied with a stride of 4. So it's going to jump 4, 4, 4, and so on. And now they've applied a formula which can be used to determine the output volume dimensions. And basically what you do is you take the number of dimensions of your input minus the number of dimensions of your filter, and then divide it by the stride which is used, and then you add 1 to this number, and this is basically a formula to determine your output volume. So you can also easily try to derive that formula. Then the next thing on this output volume here is the dimension is a depth 96. So they basically use 96 different kernels or filters to go over this image, right? So that is just on the first layer, 96 kernels or 96 filters, each of dimension 11 by 11. Then we get basically that first output volume. Then what happens next here is what is called an overlapping max pool. So we saw these pooling layers we saw before. We saw this max pooling layer, and I told that usually the stride of these pooling layers is the same as the pool size, right? In this case, this is not true. So here the stride is taken as 2 instead of 3, so you have a bit of overlap in your pool. Still, you see that also again the dimensions get reduced. Right? So you get here again a formula for, in this case, computing the reduction of dimension. Then we are again back to applying a convolution, right? So we have applied that pooling layer first, we have that volume, then we again apply convolution, this time 5 by 5 with a padding of 2, and this time we apply 256 of those filters. So again, you can basically again apply the same formula to find the output volume in this case. And this way we continue again with a max pooling layer, then again a convolutional layer, and then the image continues here. And this way, okay, we again a convolution, and what you basically are seeing is that we are sort of slowly moving towards a volume which is becoming very long and with a lot of filters. Then finally here, from this volume on, we are applying fully connected layers, right? So we're applying 2 fully connected layers, and in the end, we are ending up with a softmax over these 1000 final dimensions, like that. And so basically what we have is we have a very deep network, right? So just to get that clear, so let's zoom out a bit. So we have here one convolution layer, a max pool layer, convolution layer, again a max pool layer, convolution layer, and especially the deepness, or especially the difficulty here is in all these weights basically, right? Because here the max pooling layers don't really matter because they don't have weights, but all of these convolutional layers have weights. These fully connected layers obviously have weights, and all of these things have to be computed, have to be learned. So, and really the breakthrough there was that by applying this lot of data with this intelligent way of computing these convolutions, they were able to train that system. Right now, now one question which you should actually have is why would you first start with 11, then go with 3 times 3, then 5 by 5, then 3 by 3? So it's somehow a sort of magic numbers there, right? Where do they come from? And in a sense, that is still a bit the case. So there is still a lot of things which you don't really understand why they work, but they still sort of do. And a lot of research is going into trying to understand this better, but we do understand some things. Okay, so for example, we know that smaller filters, right? So things like 3 times 3, 5 by 5, and so on, are typically more useful as bigger filters, right? So, and that is also because they are stacked on top of each other. So when we look at one of the filters here, let's say this 3 times 3 filter, it's stacked on top of all the other things. And if you sort of recursively look at it backwards, it's depending on a large region of the image, right? So that means that even though you have only a small filter, it actually sort of comes from a big part of the image. But a lot of it is still just sort of experimental and trial and error until you find a reasonable setup. And so quite a bit of the evolution after this 2012 paper was just about sort of shaping the network a bit differently, and now you get a slightly better performance. Okay, so this was basically the example of AlexNet. So basically you saw a very deep architecture, but still it was just using all these basic ideas which we explained. And yeah, you can find a lot of other networks which have a similar idea behind them. Okay, so let's shortly summarize about what we have been talking about today. So first, with an introduction, we were discussing about why these convolutional architectures are needed. Right? And we looked at a one-dimensional case, and there we really went deeper into the reason why they are needed. And the main reason was that if you would use an MLP, like similar as we had done before, you would just fail. right? You would fail because this network becomes too big. It's impractical to train. You would need so much data, and basically you lose the ability to recognize certain features if they do not occur exactly in the same place as they had occurred in your training data. So with an example of sound, we then saw different features. Then we went to the two-dimensional case, where we applied the same things. So things like filters, padding, having deeper nested structures, and so on. And then we saw an example architecture, which was AlexNet, and discussed that there are also further developments on this. So from this presentation, the main takeaway is basically that you can have deep learning models which can themselves extract features from data, and can then also be applied in higher dimensions.